All right, today we're going to talk about a piece of tech that's, well, it's pretty much hiding in plain sight. It's called computer vision, and it's exactly what it sounds like. The science of teaching machines to see, to understand, and to make sense of the visual world, just like we do. So, how in the world does that actually work? Let's dive in.
So yeah, that's the big question, right? How do you actually do it? How do you take a machine, which is really just a bunch of circuits and code, and teach it to understand a picture? I mean, this is one of the biggest, most massive challenges in all of AI, mostly because we're trying to copy something our own brains do completely automatically, without us even thinking about it.
And, when I say our brains do it without thinking, I'm not kidding. Our biology is literally optimized for this. Get this. A staggering 50% of the human brain is dedicated, in one way or another, to processing visual information. Half! That is a huge amount of our biological hardware, and it sets an unbelievably high bar for any machine that's trying to do the same thing.
And it's not just about the sheer processing power. It's about speed, pure mind-bending speed. The human brain can identify an image we've seen for as little as 13 milliseconds. Think about that. That's faster than a single frame of a movie flashes on screen. It's a kind of instant understanding that is, well, it's just wild.
And if that wasn't enough, our visual memory is just staggering. I mean, studies have shown that we can remember thousands, literally thousands, of different pictures with over 90% accuracy. So yeah, that's the benchmark we're talking about. Massive processing power, insane speed, and almost perfect memory. That is what computer vision is trying to compete with.
Okay, so how does a computer even start this whole journey? Well, it all begins with turning the incredibly rich, continuous analog world all around us into a language that a machine can actually understand. And that language, it's just a big grid of numbers.
The whole process is called image acquisition, and it's pretty straightforward when you break it down. First, you need a light source, right? Illumination. That light bounces off whatever you're looking at. Then, a camera comes in, captures all that reflected light, and projects it onto a digital sensor. And that projection, that's the raw data. That's what's about to become a digital image.
And this is where the real magic, the translation, happens. The best way to think about it is like you're creating a mosaic. First, you have a process called sampling. This is basically just laying down the grid, figuring out where each little tile or pixel is going to go. Then you have quantization. That's the part where you pick a specific color for every single one of those tiles. And just like that, a smooth, continuous scene from the real world gets turned into a finite grid of colored dots.
Now, in its most basic form, you get a grayscale image. It's super simple. Each pixel is just one single number. That number represents how bright it is on a scale, from pure black all the way to pure white. So for the computer, it's really just a big two-dimensional grid of brightness values.
So what about color? Well, to get color, you basically just stack 3 of those grayscale-style grids on top of each other. A digital color picture is really just 3 separate layers. One layer for how much red is in each pixel, one for green, and one for blue. So again, to the computer, it's not a picture of a sunset. It's just 3 distinct grids of numbers.
And, the power of that simple 3-layer system is, well, it's immense. By combining different values for red, green, and blue, usually each on a scale from 0 to 255, a computer can represent over 16.7 million different colors for every single pixel. It's incredible.
Okay, so at this point, the computer has its big grid of numbers. But here's the thing. Raw data from a camera is often messy. It's kind of like a photo you took in bad lighting. So the next absolutely crucial step is to clean that data up and turn it into something genuinely useful. So why is this step so important? I mean, why bother? Well, because this kind of processing can pull out details, making an image way clearer for a person or for another computer program to look at. It can filter out that weird random noise you sometimes see from the camera sensor, or even help fix a photo that came out a little blurry. The whole point is to make the data better, cleaner, and way more reliable.
Let's look at a super common example. We've all done this, right? You take a picture and it just comes out too dark. Everything looks kind of gray and washed out. Well, to a computer, what that actually means is that all the brightness values for the pixels are crammed together in a really, really narrow range.
But there's a really clever trick called histogram equalization that can fix this. What it does is it looks at all the brightness values in the picture, sees how they're all bunched up, and then it basically just stretches them out to cover the entire available range, all the way from the absolute darkest black to the absolute brightest white.
And the difference it makes is just dramatic. By spreading out all those values, details that were totally lost in the shadows or washed out in the highlights suddenly just pop. The image now has so much more useful information packed into it than it did just a moment before.
All right, now for what is honestly the biggest leap of all. We've managed to get from the real world to a nice, clean grid of pixels. But how on earth does a computer go from that grid of numbers to actually understanding what it's looking at?
This really gets the core difference between what we call low-level and high-level vision. See, low-level vision is all about the pixels themselves. What's their color? How bright are they? But high-level vision, that's the holy grail. That's using all that pixel data to identify real, meaningful objects. Like that's a bowl, that's a person, or that's a car.
So the whole process starts by hunting for the most basic building blocks it can find. The computer scans the entire image, and it's looking for places where there's a sudden change in brightness or color. And these sudden changes, we call them edges. They are, for all intents and purposes, the fundamental outlines of everything in the picture. So, once the computer has a map of all the edges, it starts putting them together, kind of like puzzle pieces, to find more complex features. Where two edges meet, that's a corner. A repeating pattern of light and dark, that's a texture. It's almost like the computer is slowly, piece by piece, building up its own visual vocabulary. And at the very end of this whole pipeline, the final output is a symbolic, human-readable description. The system isn't seeing pixels anymore. It's spitting out a list of actual concepts. The machine has, in effect, translated that giant grid of numbers into a simple story about what's actually in the picture.
So, okay, why does any of this matter? Well, this incredible journey from a pixel to actual meaning is what's powering some of the most game-changing technologies out there today. But as we're about to see, it is still an incredibly difficult problem to get right. I mean, think about it. Computer vision is the tech that lets a self-driving car spot a pedestrian crossing the street. It's what helps a doctor analyze an MRI scan to find tumors. It's the engine running the facial recognition that unlocks your phone, and it's the smarts inside a security camera that can spot something unusual happening. It's everywhere.
But there are still massive challenges. I mean, the same object can look completely different if you just look at it from another angle or if it's farther away. Heck, a simple change in lighting can literally change the value of every single pixel in an image. So, building systems that are tough enough to handle all of this chaos from the real world, well, that's where all the cutting-edge research is happening right now.
And all of this leaves us with one last big question. We are, without a doubt, building machines that can see, that can recognize, and that can interpret our world. So as this technology gets more and more powerful, the real question isn't just about what the machines can see anymore. It's about how this will all change the way we see them, and maybe in the end, how we see ourselves.